What if I told you the universe is way bigger than you ever imagined, and we're just starting to see it? Imagine looking up at the night sky, thinking those tiny pinpoints of light are all there is to the cosmos, only to discover that behind each one lies billions of years of history, entire galaxies and cosmic structures stretching across incomprehensible distances. For centuries, humanity has peered into the heavens with curiosity and wonder, but we were only scratching the surface. Enter the James Webb Space Telescope, the most powerful eye humanity has ever sent into space. Unlike anything before it, Webb sees the universe in infrared, peeling back the veil of cosmic dust and allowing us to witness the earliest chapters of the universe's story. With Webb, astronomers have begun creating the deepest, most detailed maps of the universe ever made. Maps that reveal not just stars, but the vast cosmic web of galaxies and dark matter that hold them together. These maps are already challenging what we thought we knew. Webb has spotted galaxies forming faster than we ever predicted, massive spiral galaxies appearing in the universe's infancy, and even the invisible scaffolding of dark matter shaping everything we see. Every discovery pushes the boundaries of our understanding, making us rethink the universe's true scale and our place within it. Before we dive deeper, make sure to hit that subscribe button for Evolvex, and don't forget to like and share this video because the journey you're about to take is one your friends will want to see too. By the end of this video, you'll see the universe in a way most people have never imagined. You'll travel back in time to the first few 100 million years after the Big Bang, meet galaxies that are billions of light years away, yet shine brightly through the cosmic darkness, and witness the invisible threads that hold the cosmos together. Prepare yourself because the universe you think you know is only the beginning of an adventure that stretches farther, deeper, and more astonishing than anything you've ever imagined. Why the universe's scale is hard to imagine. When we talk about how big the universe is, we're really dealing with distances that are almost impossible for our brains to picture. Scientists use a unit called a light year to measure cosmic distances. 1 light year is the distance light travels in a year, which is about 9.46 trillion kilometers. When we say a star is 10 light years away, that means its light took 10 years to reach us. But the objects Webb looks at are not merely tens or hundreds of light years away, they're billions of light years distant, and their light set out long before Earth or even our solar system existed. That staggering scale is the first thing that makes the universe so hard to imagine. Astronomers often talk about the observable universe, which is the portion of the whole universe from which light has had time to reach us since the Big Bang. That observable bubble around Earth is about 93 billion light-years in diameter, many times larger than the roughly 13.8 billion-year age of the universe might lead you to expect. The reason for this apparent contradiction is cosmic expansion. Space itself has been stretching since the Big Bang, carrying galaxies with it. So even though light began its journey when the universe was young, the space between us and that light source has expanded dramatically since then. To make that feel more tangible, imagine the universe like a balloon with dots on its surface representing galaxies. As you blow up the balloon, the dots move farther apart, not because they're moving on the balloon's surface, but because the surface itself is stretching. In the same way, space has stretched over billions of years, so distant galaxies we see now are far farther away today than when they emitted the light we detect. This stretching of space and the light traveling through it is what astronomers call cosmic expansion. One direct consequence of cosmic expansion is something called redshift, which you've probably heard mentioned in Webb discoveries. As light travels across expanding space, its wavelengths get stretched, shifting them toward the red end of the spectrum. The farther a galaxy is, the more its light has been stretched, and this gives astronomers a powerful way to determine both distance and how far back in time we're seeing. That's why Webb, with infrared sensitivity tuned precisely for this stretched light, can see deeper into the universe than ever before, because until now, much of this universe was invisible to us. But Webb changed that. James Webb Space Telescope. The James Webb Space Telescope is not just another telescope, it's a revolutionary observatory designed to push the boundaries of human knowledge. Unlike traditional telescopes that see invisible light, Webb was built to observe the universe in infrared light, which allows it to penetrate cosmic dust and gas that would otherwise block our view. Infrared light also carries the stretched-out signals from extremely distant galaxies, whose light has traveled for billions of years and whose wavelengths have been stretched by the expansion of the universe. That's why Webb can detect the faint glow of galaxies born just a few 100 million years after the Big Bang. Compared with the Hubble Space Telescope, JWST is far deeper, sharper, and farther reaching. Hubble paved the way with breathtaking visible light images of nebulae and galaxies, but Webb's mirror is 6.5 meters wide, nearly 3 times larger than Hubble's mirror, giving it the ability to collect far more light and see much fainter and more distant objects. Webb's infrared range extends much farther than Hubble's, allowing scientists to look not just at nearby stars and galaxies, but truly into the cosmic dawn when the first structures in the universe were forming. Webb carries several advanced instruments that make this possible. Its near-infrared camera, NIRCam, captures stunning high-resolution images of distant galaxies and star nurseries, while the mid-infrared instrument MIRI detects heat from dust and the earliest star-forming regions that are invisible in ordinary light. Together, these instruments let astronomers study galaxy formation, dark matter lensing, and the evolution of cosmic structures in unprecedented detail. Imagine seeing light that began its journey when the universe was just about 300 million years old, a time when the first galaxies were igniting like embers in the cosmic dark. That's the promise of JWST, to reveal how galaxies emerged, grew, and shaped the universe we see today, opening a new frontier in our understanding of the cosmos. Deepest look back in time. When astronomers say Webb is looking back in time, they aren't talking about science fiction. They're talking about light travel time. Because light has a finite speed, when we observe a distant galaxy, we see the light that left it billions of years ago, long before the Earth even existed. The farther away the galaxy is, the older the light we observe, and thus the farther back in time we're peering. With Webb's infrared vision, we can see light that has traveled across the expanding universe for more than 13 billion years, revealing galaxies as they appeared when the universe was only a few 100 million years old. NASA explains how Webb's deep surveys allow us to fill in the early chapters of cosmic history by literally seeing those ancient light signals. One of the most extraordinary examples of Webb's reach is the galaxy JD's GS ZES 140, which existed roughly 300 million years after the Big Bang, making it one of the most distant and earliest galaxies ever observed. What's surprising is not just that Webb can detect such far-off light, but that some of these early galaxies appear larger, brighter, and more mature than many theoretical models predicted was possible in such a short time after the universe began. Observations show that these galaxies have already formed many stars and have structures far more developed than expected. Webb has also identified other distant galaxies like Uncover Z13 and Glass Z12, which shine from an era about 350 million years after the Big Bang. These findings are reshaping our understanding of how rapidly galaxies emerged and evolved in the early universe. Scientists describe these early systems as akin to meeting teenagers in a world of toddlers' galaxies that seem surprisingly active and grown up in a cosmic infancy we once believed was quieter and simpler. As astronomers continue to push Webb's observations deeper still, each discovery adds tension to our cosmic story, challenging previous theories about how fast the first galaxies could form and grow. What we're learning now wasn't even imaginable just a few years ago, and Webb's deepest gaze continues to stretch our sense of time, space, and the very beginning of everything. Beyond just stars. When we look up at the night sky, we see stars and galaxies, but the universe is much more than those twinkling points of light. Most of the matter in the cosmos isn't visible at all. It's made of dark matter, an invisible substance that doesn't emit, reflect, or absorb light, but outweighs all normal matter combined and forms the hidden backbone of the universe. Scientists infer its existence not by seeing it directly, but by observing how its gravity bends the light from distant galaxies, a phenomenon called gravitational lensing. This effect works like a cosmic magnifying glass. When light from a more distant object passes near a massive cluster of matter, the light's path is bent and distorted, revealing clues about the otherwise invisible mass that caused the bending. With the James Webb Space Telescope's unprecedented infrared sensitivity and sharp vision, astronomers have created the most detailed dark matter map ever of a region of the sky, using how light from hundreds of thousands of background galaxies is subtly distorted. This map doesn't show dark matter directly, because dark matter emits no light, but instead shows how it shapes the universe's structure through gravity. Webb's data reveals filaments and clumps of dark matter forming a vast interconnected cosmic web, a structure along which galaxies and galaxy clusters are strung like beads on invisible threads. Scientists describe this as seeing the invisible scaffolding of the universe for the first time with such clarity. Understanding this cosmic web is essential because dark matter's gravity pulled ordinary matter together in the early universe, guiding where galaxies formed and how they evolved over billions of years. Without this dark matter framework, stars, planets, and even entire galaxies might never have come together. These maps help scientists refine models of galaxy formation, showing how matter flows along filaments into dense clusters and how the universe's large-scale structure emerged from tiny density differences after the Big Bang. As Webb continues to map deeper and farther, it expands not just what we see, but how we understand the very architecture of the cosmos. The true scale of the universe. It might sound impossible at first. The universe is estimated to be only about 13.8 billion years old, yet the part of the universe we can observe stretches roughly 93 billion light-years across. How can that be? The answer lies in cosmic expansion. Space itself isn't static. Since the Big Bang, space has been stretching, carrying galaxies with it, so that light emitted billions of years ago has traveled through a universe that was continually growing larger. Because of this expansion, the regions from which light has reached us today are now much farther away than they were when the light was first emitted, and that's why the observable universe is far bigger than the universe's age would suggest. A simple analogy is to picture the universe as the surface of an inflating balloon with dots on it representing galaxies. As the balloon expands, the dots move apart, not because they are traveling across the balloon's surface, but because the surface itself is stretching. In the same way, the space between distant galaxies has expanded while light made its long journey to us. What started as light emitted when the universe was young is now spread across a much larger distance by the time it reaches our telescopes, giving us a snapshot of the early universe that is both ancient and enormously distant by today's standards. The James Webb Space Telescope dramatically extends this view by using its powerful instruments to detect infrared light from these ancient red-shifted sources, letting us see farther back and in more detail than ever before. Large surveys like Cosmos Webb have charted nearly 800,000 galaxies across cosmic history, from relatively nearby to the edges of observability, refining our picture of cosmic structure and showing how matter has clumped and evolved over billions of years. Every new distant galaxy Webb detects pushes the frontier of the observable universe outward and deepens our appreciation of the vast cosmic tapestry we are now finally beginning to see. Surprising discoveries and challenges to theories. One of the most exciting things about the James Webb Space Telescope isn't just that it sees farther, it's that it has revealed a universe that often doesn't behave the way our theories predicted. Cosmologists expected the earliest galaxies to be small, simple, and slowly building up their mass over hundreds of millions of years. Instead, Webb has found that some ancient galaxies were already large and complex much earlier than expected, suggesting that cosmic growth in the young universe happened faster and more efficiently than our models predicted. Take the example of several galaxies observed when the universe was less than 1 billion years old. These infant systems show chemical maturity, meaning they already contain significant amounts of heavier elements like carbon and oxygen, which should take many generations of stars to produce. Astronomer Andreas Feist put it in terms anyone can relate to. It's like seeing 2-year-old children act like teenagers because these galaxies behave in ways we didn't expect so early in cosmic history. Webb has also revealed some ultramassive galaxies in the early universe that are nearly as massive as the Milky Way, even though they existed when the universe was still very young. These results suggest that stars and galaxies may have grown in mass much more rapidly in the early cosmos than previously thought, posing real puzzles for star formation theories and simulations of early galaxy evolution. Another dramatic twist is the discovery of surprisingly well-structured spiral galaxies in the early universe, objects with features similar to modern galaxies but formed when the universe was just a few billion years old. Astronomers describe these early spirals as cosmic cousins of our Milky Way, but their existence challenges the long-held view that such ordered structures should only arise after much longer periods of cosmic time. All of this is fueling a subtle but powerful shift within the scientific community. Instead of simply filling in gaps in our knowledge, Webb's data is forcing researchers to rethink how quickly galaxies grow and what physical processes dominated the early universe. And that's huge for cosmology, because every time we adjust our models to fit what Webb observes, we gain a deeper insight into the fundamental workings of the cosmos and the story of how everything came to be. How this changes our perspective. The discoveries from the James Webb Space Telescope don't just rewrite our textbooks, they fundamentally change how we see ourselves in the universe. For centuries, humans have looked up at the stars, wondering if we are alone and what it all means. Now, we realize that every galaxy, every star, every tiny speck of light carries a story that is billions of years old, a story that Webb is helping us read for the very first time. Each ancient galaxy we observe reminds us that the universe is far more vast, intricate, and dynamic than we ever imagined. These revelations shift our cosmic narrative. We are small, almost imperceptible, yet part of a larger, structured cosmos connected by invisible threads of dark matter and shaped by forces that operate across unimaginable distances and timescales. Knowing this expands our sense of wonder and humility, as well as our appreciation for the delicate balance that allows galaxies, stars, and planets to exist. And the adventure is just beginning. Webb continues its mission, surveying ever deeper regions of space, promising to uncover the earliest stars, the formation of primordial galaxies, and the hidden structures that shaped the cosmos. Every image it captures is a doorway into a universe that is alive, evolving, and waiting to teach us more about our place within it. Future discoveries and what to watch for. The James Webb Space Telescope is far from done. Upcoming surveys like Cosmos Webb and JADES promise to map vast swaths of the universe in unprecedented detail, revealing thousands of previously unseen galaxies and structures. Scientists hope these missions will uncover the very first stars, detect the earliest black holes, and even provide new clues about mysterious forces like dark energy that shape the expansion of the universe. Every new image from Webb is a potential game changer, capable of rewriting what we